two gentlemen. So for those of you coming in still sitting down, move on to the front. No need to sit at the back. And Steve Surfling is with Cirrus, and he's been head of project management for the jet. So of all the people in this room, he probably knows more than I do, that's for sure. So Steve?
Good afternoon, everybody. I will just be introducing, making a few comments before Paul and Dave start the presentation. The thing I'd like to talk about first is some of the history of the jet just in the recent years. And in 2007, I think you all probably remember that we unveiled the jet. And then last year, a week ago, next Friday, we flew it for the first time. And then later that week, about a week later, when you all were here, we had a position holders event and named it. We then named it the SF50 Vision. So most of the time marketing calls it the Vision, and most of the time engineering calls it SF50. So you'll hear both of those, but they're the same replacement name for the jet. So this year, we thought as Brent said this morning, there's been quite a few changes at Cirrus, and one of the changes, major changes at Cirrus from our perspective, was that we downsized quite a few people, but we stayed focused on the jet. So what that really meant, and you've heard this many times and we'll go into it, is that we reduced some of the focus on the SR2X and put those people on the jet. So that one of the things that came out of that was we brought all of the engineering teams together, and the result of that was a very focused engineering team with their primary mission was to continue developing the jet. And V1, as you know and have seen last night, which these guys have a hard act to follow as far as I'm concerned, that flyover was pretty impressive, I thought. But these guys were part of, have been at Cirrus for a long time. I think they'll introduce themselves and tell you something about that. But Paul Bray now is Vice President of Engineering, and Dave Rathbun is the SF50 Chief Engineer. They've been around Cirrus for a long time. Mike Van Stoggen and I are still very much a part of the jet team, if you will. So you'll still see us and hear us. But because of the transition of going from a rapid prototype to a focused production intent design, I thought the best thing to do was to have the engineering leads in our team come up and talk about some of the differences between rapid prototyping and very early flight testing, as we've been doing over the last year, and start talking more about the disciplined approach to certifying this airplane. So with that, I'd like to introduce Paul Bray, who will start it.
All right, thanks, Steve. Can everybody hear me okay with this thing? All right. This is actually kind of funny for me because what did I do? Of course. I've been around Cirrus for quite a while, and I bet nobody's ever heard of me. Annie has. I started out as the chief of structures on the SR20, so that was 13 years ago. And since then, I was a program manager for the SR22 through that program, through certification. And then I've managed the design engineering team basically since then through the G2 and the G3. I know a fair amount about your airplanes, probably as much as anyone alive. But I'm a little more of an introvert, I guess, than the rest of Cirrus Engineering Management. But anyhow, I guess it's my time to stand up here and talk about what people are doing here. And also, I want to introduce I want Dave to introduce himself at the same time too, because he is an integral part of this airplane program. In fact, he's the heart and soul of it at this point.
Hi, my name is Dave Rathbun, the chief engineer for the jet, and I've been at Cirrus for a long time. Paul and I worked side by side. It's kind of funny when we first started doing the SR20 program. We both kind of entered it at about the same stage where we were picking up a rapid prototype and turning it into a production design, and we worked hand in hand. I was doing a lot of the airframe design, and he was the stress guy, and so there was a kind of a love-hate relationship with that, but all very necessary and very rewarding after it's all said and done.
All right, we're gonna go through this update, and Dave's going to do part of it, and I'm going to do part of it. So, typically, when an engineer comes and does an update on a program, they show a bunch of CAD models and they talk about detailed design and the decisions that they made, and they give you these lists with 100 bullets and talk about each one and overrun by 15 or 20 minutes or an hour. But instead, I guess I was trying to think about, if I were you guys, what would I want to hear? What do you want to know? What do you want to know about the program? So what I'm going to talk about is really, what does an airplane program look like? How does it actually work? Where are we? Where is the SF50 in this project? What have we been doing for the last year since the airplane flew and you heard from us? And are we doing a good job at it? And then maybe a few details about the design. So I'm going to start out with this little eye chart. This is our product development system. And it works like most product development systems. I don't know if I can do this or not, if I can point, but it goes through this early stage where you're trying to figure out what'll work. You do some concepts. You do a little bit of development. You test it a little bit. You try to decide if it's really going to work. Then you move on to the design. The design is kind of the heavy lifting. It's where the real design comes from. Well, right now, I would say this is where we are in the program. The red line is really where we are. We are in the transition from what Steve called the rapid prototyping stage, from the concept and development stage into, we're going to certify this airplane and we're going to make it happen now. Now, I put the little distribution in there because I'm an engineer, and everything's really a continuum. There's no absolutes. So some of the work has progressed further and some of it lags behind. That kind of explains that. The next question when you look at that is, holy cow, they're only half done. And that's what you think, but we're not half done. The design part of this, the design part, the pilot part, and production. You care about production. Everybody cares about when we actually get the airplane built. But most of the hours actually go into the design part. The design part culminates with a flight test airplane that's through flight test, and we get our type certificate. The interesting thing about the design part is that it's really resource driven, whereas those first three phases that you saw that we've gone through, they're really calendar driven. They're driven much more by the amount of time that it takes to learn. So anyhow, how are we going to finish this? The critical path in this project is really about, the first part of it is the design, tooling, and fabrication of the flight test and ground test vehicles. That's the hard part. Then we got a flight test program, and then since it's a jet now, we have a new requirement that we've never had before called functional and reliability flight testing, which means we basically have to build production units and we have to operate them 200 or 300 flight hours with FAA personnel on board, and they determine whether or not we designed it well enough to go into service. So anyhow, you can get your calendar calculators out here now. This is what we really think the program is going to take at this point. This phase is going to be 18 to 21 months. We're thinking 12 to 15 months of flight test and another 3 to 6 months to do the F&R testing. So when you add all that up, that puts us somewhere squarely in somewhere between April 12 and January 13. That's truthfully where I think we are in the program. And I think that we are actually staffed to do that at this point. Back to this. Okay, so we finished design, but we got this whole pilot phase to go through before we start producing airplanes and you all start getting your airplanes. Well, the Cirrus way is to do the pilot program during the design phase. So by the time that we build flight test airplane and enter flight test, we will be converting that to production tooling. We'll be building production pilot airplanes. And our plan is the day we get the type certificate and the day we finish the functional and reliability testing, we are ready to start delivering airplanes and we're ready to start producing airplanes. And that has basically been our MO on every project that I've ever been on at Cirrus, which is all of them. So the next question is, what have we been doing for the last year? And Dave wants to talk about this.
Thanks, Paul. Well, to basically sum it up, we've been flying V1, our vehicle, flight test vehicle 1. And what that is, to talk philosophically a little bit about what V1 is. V1 is not the airplane that we intend to put in production, but it is a critical tool to help us determine what the configuration of the airplane that we will ultimately put into production. So with that, it started out as a fairly quick concept, and as we've been flying it, we've been learning an awful lot about the design and learning an awful lot about how good our analysis and estimating techniques are. So we flew it about a year ago, and since then we've put landing gear doors on. We've changed the design of those. They affect the handling qualities of the airplane a little bit. There's been some refinement in that. Another big part of the test program is envelope expansion in both speed and CG range. So we've been looking at the stalling qualities and the flying qualities, forward CG and aft CG, and finding out where those limits are. And one of the things that we've been learning from that are some refinements to the flight control systems, the geometry of the elevator and stabilizers, ailerons, to make the airplane a lot more of a good flying quality airplane. So we've how do you work this thing? Okay, there we go. I'm sure you guys on the web end can't see the pointer on here at all, but fall of 08 we installed the spin chute, and we've also been experimenting with different nozzles, and that plays into the flying qualities a lot and also the performance of the airplane. Also look at simulated ice boots. Those were installed to gauge the relative cruise performance impact boots would have, and helped us tailor a very refined laminar flow boot installation, where we've changed the wing shape, the wing airfoil shape, to accommodate the boots so that we have very little reduction in drag. We've also been looking at Dutch roll qualities of the airplane and looking at different stabilizer shapes. We've ultimately come to something that we've called the X-tail, and I have another slide on that, and I'll talk a little bit more on that. Also, we've put vortex generators on. We've just installed new avionics. We've also installed a different configuration flap, which should save about 30 to 40 pounds over a conventional tracked Fowler flap system. So we've been pretty busy. I'm going to talk a little bit about some of the performance results that we've been getting from our flight test airplane, just to give you a picture what the capability of the airplane will be. But first, I want to describe the NBAA IFR range profile. When you're comparing this jet to a piston airplane, there's a fundamental difference in the way that you calculate the range. With a jet, you also have to consider this 100-mile diversion to an alternate for a small jet, where when you're talking about a single-engine piston, it's generally absolute range with a 45-minute reserve. So this 100-mile difference makes the direct comparison a little difficult. But I've got a slide showing what the SR-22 would look like with this NBAA IFR range profile. This is a little bit of an eye chart. The specific range of the airplane is a function of airspeed. Basically, our fastest cruise speed is at a higher fuel flow, shorter range. That's around 300 knots, and then the slowest highest range is around 210 knots. Burns basically about 33 gallons per hour at 210 knots. Carries about twice the load of an SR-22 at that speed. So, and it's an airplane that's roughly twice the size. So it's a similar basic performance of basic efficiency of an airplane. But then with the added thrust, you can go much faster. So what this looks like in terms of cruise performance versus payload versus range might be kind of hard to see in the lighting in this room, but we've got a blue line here which represents the highest speed, and a green line which represents the lowest speed. Lowest speed of course, a little over 1,400 miles range with full tanks and about 400 pounds of payload. And then the highest speed, a little bit more than 400 pounds of useful load, and about a 1,000-mile range at that speed. So I just want to focus in on this 300 knot, which is our fastest number. This is the one that we've been talking about the most. We want to be able to go about 1,000 miles at about 300 knots and carry about 400 pounds. When we compare that to the SR-22, we can see basically the difference in the capability, range and payload. The SR-22 is down here at roughly 200 knots, with that MBAA range is just short of 800 nautical miles for the same 400-pound payload, versus the jet, which with that same 400-pound payload at 300 knots will take you over 1,000 miles. So quite a bit more capability with the jet. Touch on some of the design improvements, lessons learned from the V1 test airplane. We've smoothed the wing to fuselage joint, and there's a lot of work that's typically done on airplanes in this area. But basically that comes in two parts. One of them is the shape of the fairing between the wing and the fuselage. But another one is the shape of the airfoil, the inboard section of the wing. As the air flows around the fuselage, that flow field is disturbed over what a wing is traditionally designed with no fuselage, so it's in clean air. But once you disturb that with the fuselage, what the airfoil sees is different. And so we've shaped the inboard section of the wing to accommodate that flow field around the fuselage, and that results in a significant reduction in drag. We've added stabilizer fins. Talk a little bit more detail on that. We've changed the sweep and position of the stabilizers. That is done to reduce weight and improve the handling qualities. We also removed the right side door. Our initial prototypes and concepts had two doors, but we've found that that's to accommodate that is a significant increase in empty weight of the airplane. So the reduction in complexity of that makes it a more reliable airplane and able to carry a lot more weight. We've changed the shape of the nose, and there's a number of reasons why we've done that, but one of the things is to allow us to install the EVS camera flush. When the airplane was originally designed, the concept of EVS wasn't part of the program. So we've added that, and we want to make that a good low drag installation. There's also some benefits in air conditioning packaging, cap packaging, landing gear, etc., that changing that nose shape gave us. We changed the design of the flaps, as I said, and the purpose of that was to take about 30 or 40 pounds out of the airplane and also result in a much more reliable, less complex, safer system. We've changed the exhaust nozzle, and we're still iterating on that, and that's a trade-off between handling qualities and cruise performance. We'll talk a little bit more about stabilizer fins. The last slide, I could probably go on and on all day about a lot of these details, but the detail that I generally like to talk about these things are not interesting to most people. But the stabilizer fins is one that it's immediately visible. It's probably one of the most significantly easy to recognize changes that we've made to the airplane. We've had 2 or 3 different configurations on the plane, as well as 50 plus configurations that we've looked at in computational fluid dynamics models. The result of this is we ultimately want to make the airplane the lightest possible airplane. And one of the ways to get the lightest possible airplane is to put the smallest size of tail on it, which also reduces drag and makes it a faster airplane. But when you do that, you also result in an airplane that doesn't have as good of flying qualities. Another aspect of the V-tail is it has a very strong dihedral effect. So a gust of wind to the side or a side slip will make the airplane want to roll into that side slip. That stability is generally good, but with it coupled to the tail, you can get a Dutch roll characteristic that is more undesirable. One of the ways to combat that is to put a smaller dihedral on the main wing. Well, we don't want to do that because we want as much dihedral there to improve the handling qualities, as well as to reduce the unusable fuel capacity of the airplane. So there's a big matrix of trade-offs that you want to make the airplane the best possible airplane. And one of the nice things about this dual tail, this dual stabilizer fin design, which we've been calling the X-tail because if you look at it straight on from the back, it looks like an X from the stabilizers, the main stabilizers and the stabilizer fins, is that it reduces dihedral effect. So it takes away some of that adverse dihedral effect that we get from the V-tail and returns that in the form of better handling qualities with a lighter weight structure. There's another side benefit is that by having a horizontal component to those stabilizer fins installed down low on the airplane at high angles of attack, they become much more effective and make for a better pitch down moment in the stalling regime. So we kind of get a double benefit from those with better stalling qualities and better yaw qualities.
Okay, now it's my turn again. Airplane programs. You hear about airplane programs, and let's talk about the 787 for a second. It's a horrible airplane program, right? It's years late, it's way over cost, and now it's on to another delay again. Eclipse was year after year of delay, promises and delays. The A380, I mean, probably 3/4 of the airplane programs that we know of in our time had really serious problems in them. And airplane programs get in trouble because people want too much. And it would be easy to say that, this airplane, this SF50, the Vision jet, it's promising a great deal. And we're a relatively young company. Do you think we can deliver it? Well, airplane programs get in trouble there's really 3 big reasons. One is the airplanes get way too heavy. People can't estimate the weights properly, or it's harder to do than they thought. Another is they have complex aerodynamics, or a lot of drag, or they have a need for really high installed power. Not successful airplanes. You just never get them to work. Some airplanes are too complex and too expensive, or just maybe ill-conceived. That's my favorite one, by the way. I think they must had a stall speed problem. But, well, we're no different. We're an airplane program like every airplane program since the Wright brothers. We fight weight, we fight drag, and we fight cost. They're all opposed to each other. It's always a trade-off between those things. So where are we? We're relative to these things that kill airplane programs. Well, the weight status, the last updates that Mike and Alan did, I think they promised a 3,700-pound empty weight for a typically equipped airplane. Our objective right now in the program is 3,600 pounds, and we're 55 pounds over at 1.5%. And we have, actually, I think the 1.5% is going to be pretty easy to get back. What we really want is we want something less than 3,600 pounds. But we're going to get that. We're going to get that by, we just finished a full-scale wing test on a development wing. This is something most airplane companies would not do. We built up a structural test wing and we tested it, and we actually purposefully underbuilt it and tried to predict the failure. And what we learned from it is that we can take a significant amount of weight out of the wing. At the same time, we're evaluating, we're trying a concept to build a single-piece pressure hull for the fuselage, which would take all the joints, basically all the joints, the structural joints out of the pressure section of the fuselage, and we can get a bunch of weight out there. And then finally, we drive weight targets down to the subsystem and engineer level, and we manage the team with a goal to reduce those weights. We're not going to let this airplane just turn out to be however heavy it turns out. We're going to manage this thing to the end. Drag. The drag situation, I think, really looks quite good. The V1 performance is really only about 3% total drag shy of what it needs to for us to meet the range goals. And anybody, I don't know if you guys look closely at that X-tail picture. I mean, the back of the fuselage was tufted. Airplanes in 1G level cruise flight, and half of those telltales were standing up. They weren't flowing back. So that wing rut fairing and the inboard wing contain quite a bit. In fact, we think probably as much as 9 or 10 of these aerodynamics people talking drag counts. 9 or 10 drag counts. But what we really want is we want to go into the design. We want a tool with a 3% margin, because airplanes, as airplanes mature, they only get heavier and they only get slower. So we've got to be starting from a place where we're going to meet those goals. And the way we're going to do that is this inboard wing loft, the wing rut fairing. A lot of drag can be designed into an airplane from cooling, for bleed air cooling and air sources, air inlets and air outlets. So we're going to manage those carefully. And we have the advantage now of a relatively sophisticated computational fluid dynamics analysis that tells us we can compare design changes and get relative differences in drag. We may not be able to predict absolute numbers perfectly. We get great relative numbers, and we can choose configurations that are lower drag without having to go fly them and guess. So I fully expect to meet the cruise range, the range and speed goals, and in fact, I'd be surprised if we didn't beat them. Cost, the big question. When I think about what the price of the airplane is going to be to the customer, to me it's going to be dependent. At that point, we're going to have a bunch of sunk cost. So at that point, it becomes dependent on what the bill of materials that goes into it is, what the direct labor component of it is, what the manufacturing overhead component is, and then the last thing is the rate that you build it at. How many can you produce in a year? This was the Eclipse model, right? They're going to make 1,000 airplanes a year or something, and so they're going to be able to make them really cheap. Well, we understand the direct labor component and the manufacturing component. It scales almost exactly from the airplanes that we build now. We have a great factory. We produce efficient airplanes. And our bill of materials cost, I'm going to talk about it in a minute, but the rate is really the big question. The rate that we produce them at, whether it's 100 a year, or whether it's 250 a year or 400 a year, will ultimately determine the steady state price in the market. So the bill of materials cost for the airplane, when Mike Van Stagen and Alan Klapmeyer conceived this airplane, I don't know how many years ago it was. It was probably before I was born, I don't know. But anyway, when they started getting serious about it, they did some estimates on what it would cost to do this airplane. They tried to scale what they knew from the SR-22, and they tried to understand what else goes into a jet. So we have this bill of materials cost that was estimated, 5-6 years ago. Well, we're 24% over that now. Now that's really not that bad considering inflation and quite a few other things. But since then, we've built a more comprehensive business case model of the airplane with cost assumptions built into it. And this is, we have to do this to determine whether the project's really worth doing and how we can make money on it. Well, right now the current number is about 8% over that target. That's really not that bad. And we understand that we need to reduce it further, and I have high hopes that we will. And one of the reasons that I'm really very confident that we can is that most of the high-cost components in the systems of the airplane, we only have verbal quotes from vendors. We haven't actually negotiated with them. We haven't talked about rates. We haven't done a lot of that yet. So when we get to these final supplier agreements, I'm expecting that we should be able to extract considerably lower costs than what we're estimating now. And then the other alternative is we can start trading off performance, system performance, and other performance to try to reduce costs. But the cost target is a big one. Everybody is, is it going to be $1 million jet? Well, I don't think it's actually going to be $1 million jet by the time that we get to deliveries. But it's a lot closer than I think most people would think. Some other what's really important progress. People talk about certification. Certification's a nightmare. Certification prevents people from putting good airplanes in the market. Everybody has trouble with it. Well, we've had our preliminary type board meeting last fall. There's only been 32 there's 32 issue papers or action items the FAA has taken exception to. And for those, 80% of them, we have positions and we have responses from the FAA. And we really have no differences, no significant differences between what the regulatory authorities want and what we propose to do at this point in time. And in fact, we have an interim type board meeting scheduled about a month from now, and we're going to be sitting down with our FAA counterparts and going through those issues again. So, for such a novel airplane, I think we're in a pretty good place. Tooling development. Tooling development is what paces the airplane. It's the thing that takes the longest in I don't know about metal airplanes anymore, but I know in composite airplanes, we can design an airplane a lot faster than we can build tooling and build an airplane. So this is really kind of the linchpin for getting the project done. And where we are with it is the tooling lofts for what we call master models that we make the layup tools from. They're all in some stage of final evaluation. The stabilizers, the middle part of the fuselage and the aft fuselage are pretty well locked down, and in the third quarter I suspect we're going to start cutting tools. The wing aero loft, Dave talked about, it's on its third or fourth iteration. I don't know, it's starting to become a source of irritation. Okay, 7. But we will get that. And the forward fuselage, we're considering adding some more volume up there because we want to make sure the parachute fits and we don't want to do this twice. But the important thing is that the tooling resources that we have and the pace that we can build tooling at, the queue is full. So we have time to continue working on these and refining these lofts that are going to help us without jeopardizing the program or the pace of the program. CAPS. CAPS is probably the biggest challenge on the airplane. Nobody's really ever attempted anything like this. What you see here is the scaled, the parachute is, the lower parachute represents the SR-22 parachute. The upper will be the SF50. It's 89 feet in diameter. And it is going to happen. We have studied this. We've studied this with several development arrangements with subcontractors. We have good models of this. We have a system that we know will work, actually. We have several options for it. And we have a physics-based simulation model that actually, it predicts the SR-20 test deployment performance, and we can put in the aerodynamic, the stability derivatives, the inertial properties for the SF50 and the parachute properties. And now we can design this system so we know we can do it. So that where we're at with it now is we're trying to decide what is kind of the cost and weight trade-off of that system versus how much of the total aircraft operating envelope do we want to protect. And our goal is to try to protect the envelope up to cruise, which is a much different goal than we had with the SR22 and the SR20, a much more difficult goal. Cruise can be up to 300. This is going to be a very interesting system. But I'm really pleased with the progress that's been made in the last year on this system. We will be in the wind tunnel with parachutes in this fall, and I think this winter we will be, as Dale said, bombing the desert. We have parachutes being fabricated for drop test at this point. So this system is progressing very, very well. This is kind of a fun thing, but think of the SF50 as a natural evolution from the SR22. This airplane is going to happen. It's happening. For people that didn't believe it could be done, I had my doubts several years ago too. I'm here to tell you this is going to happen. That's what we have. I guess we came up a little short on time here, but I'll take any questions that anybody has. We love to answer questions. The SR22 has 6 carbon fiber parts. Pardon? Oh, repeat the question, sure.
Yeah.
The question was what do we know about carbon fiber on the aircraft, and how much do we expect to use, and what kind of labor component do we expect on the airplane? Is that okay? The SR22 has six carbon parts in it, one of which is the main spar. The SF50 will have about 250 carbon parts in it. We've basically selected a material. It's not the material that we currently use. It's going to be a material that has a slightly lower density for the same strength. We expect to use the same kinds of manufacturing processes, which is basically vacuum bag, oven cure, 270-degree cure that we use now for our glass and carbon composites. The question actually, the direct labor component, the numbers that I've heard range from 2,500 to about 3,200 hours to assemble the airplane. Well, I think they're pushing that down close to 1,600 at this point.
One of the other things about carbon fiber, it's a capability that we have today, but since we're making so much more parts out of carbon fiber with the jet, we have to increase the efficiency of the inspection process for all of those other carbon parts. Right now, the spar is largely a manual, non-destructive inspection process that we do on every single part, and we expect to continue that level of scrutiny on the SF50 parts, but there's so much more of them that making that process more efficient is important. There's also a question that's often asked about the test airplane being made out of fiberglass, and how can a fiberglass airplane relate to a carbon airplane? The stiffness doesn't really play that much into the flying qualities, but even though the test airplane was built to an equivalent stiffness, it was designed and built to an equivalent stiffness that a carbon structure would have. So there's essentially no difference in the behavior of the airplane as if it was made out of carbon.
I think the answer to that depends on the rate or on the volume that we decide to produce it at. I would guess for the first year that we can fit into our existing facility. If the rate justifies more, we'll have to build a business case for it.
We've expanded the building before, more than once, and if we need to, we'll do it again and again.
We want to. I mean, I want to. Yeah. Right now, we would rather. Oh, I'm sorry. Is the 25,000-foot ceiling locked in, or might it be more? Right now, I would say that we want to keep it to 25,000 feet, but I would also say that we would want to have the capability to go higher at some point in the future.
The question is, what is done to the engine to make it operate more efficient at the lower altitudes where we're operating? You want to answer that?
No, I want you
Okay. The short answer is nothing. But the long answer is the design of it's a new design engine, and operating efficiency at the altitudes where the engine is designed to operate is part of the goal of that engine. So there are things that are done with bypass ratios and other things that I really don't understand with jet engines. Thankfully, I don't have to design it. But really, the challenge is to get the efficiency out of the airplane engine, the whole product, with the limitations of the thermodynamics that we have to work with.
We do know that going up to 28,000 feet does increase the range and improve the performance.
And
yeah, FADEC's a beautiful thing.
The question is what kind of growth path do we need to take to get an airplane initially certified at 25,000 feet to 28, 31, 41, 50, 60. It's kind of a complex answer, but basically each increment of higher altitude that you go, there's one more thing that you have to address. Above 25,000 feet, there's emergency oxygen requirements. There's dual pane window requirements. There's changes in the structure depending on what we select for cabin pressure differential. Above 28,000 feet, there's RVSM. There's also redundant cabin pressurization requirements. So there's really not one breakover point. It's just kind of, as you keep going, it's more and more. And we initially selected 25,000 feet because that makes the most simple airplane that we can make. And getting to a price point, a level of complexity, et cetera, to keep the program under control, that's the point that we ultimately selected, or initially selected. Probably not.
Okay. Commercial and a jet type rating.
The question is, have we defined or talked to the FAA about pilot training requirements, and will the pilot be required to get a type rating? And our training department has been meeting with the FAA to start to define what the training program is and what the requirements are, try to get an understanding of what the duration for the type rating is. It will require a type rating. There's no real latitude with the FAA in coming up with some kind of a special condition or exemption for type ratings for turbine-powered airplanes.
I think Steve wants to answer this for us.
I want to talk a little bit more about it. Is this on?
It's on.
a little bit more about that is we recognize that pilot training is going to be a significant part of this airplane. So we early on last year we contracted with Bob Wright. I don't know if any of you know him. He's retired FAA, and he worked very, very closely on the Eclipse training program. So they did some things wrong, they did some things right, and we contracted with Bob, and he told us how to develop this in the right way. So Bob worked, Bob Wright, Paul Fiducia, who's another team member of ours, and also Rob Haig, who works in our training department now. So Rob has got the prime responsibility, but we're probably going to be bringing Bob Wright back into the picture here in the near future. But we've got the syllabus started, we've got the simulator plan started, and we've got the type certificate goals and objectives started. So the next step is to bring that, like we have with the preliminary type board, bring it to the FAA and start the process of getting it approved. So we haven't done that last step, but we've done quite a lot of analysis of the upfront and even some of the syllabus work.
The question was on the chart, fuel flows at, well, let's just take a look. Fuel flows at 300 knots. Right there.
Yep, one up.
62.8, give or take.
That sounds pretty accurate. 62.875, I think it was.
Yeah, that's measured right off of, it's going to depend on how the airplane ultimately ends up. Of course, our B-1 airplane, this is based on the testing we've done on our B-1 airplane with accommodations for things that we know that we're going to put into the design that will add drag, less things that we know that we're going to put into the design that will reduce drag. We talked about the inboard wing airfoil section change, the wing root fairings. There's a number of things we're doing with antennas and gear doors, and removing the flight test boom reduces drag. So there's a lot of those things that we've made accommodation for in our analysis that reduce drag, and then things like adding the ice protection increase drag a little bit. So that's our best estimate. I wouldn't say that it will be 62.8, but it would be interesting if it is.
Yeah. What are the implications of 28,000 feet on those numbers?
Yes.
Yep.
I don't think I want to guess.
Question from the web here. What will be the cabin altitude at 25,000 and any expected impact on air conditioning with the large windows?
Cabin altitude at our maximum operating altitude will be 8,000 feet. And
Will be what?
Maximum,
8,000 feet.
Maximum.
8,000 feet.
But that's not our goal.
We would like to make that lower. A 6,000 foot cabin would be very nice, but we're not at that point yet. Effect of the large windows and air conditioning, I don't really know the answer to that.
The large windows require that you pull a bigger air conditioning load. It is considered in the design, and in fact, we have a mock-up of the cabin with that actually has the solar radiation sources built into it, and we're experimenting right now with whether or not the systems that we have will pull down those cabin temperatures and manage them.
Yeah, I guess another way to answer that is we don't really know and we don't really care. If the effect of the windows is high, then we have to increase the capacity of the air conditioning to make it a comfortable cabin. We'll do that before we put smaller windows in for air conditioning. Another question? Where are we going to put the antennas? Our current plan is we've evaluated a number of different locations, and we're going to put them on the outside. We haven't identified all of the locations for all of the antennas. We've been doing a number of different analyses to determine the performance effects of antennas on different locations. It's actually pretty sophisticated analysis. It goes way over my head. But I do know that the COM1 antenna will be on top of the nacelle somewhere, and the COM2 antenna will be on the bottom of the belly. The two GPS antennas, one of them is a GPS combo antenna. They may be in a couple of different places. The most favorable place, it's down to between somewhere on top of the nacelle or one each on top of each stabilizer. Transponder antenna, probably have one of those towards the back end of the nacelle, and then option for a second one on the bottom of the airplane. ADF and DME antennas, we have locations for the bottom of the airplane for those. I don't remember where the ELT is, but I think it's in the tail cone. And then the marker beacon is in the radome, either forward or on either side of the nose gear. Did I leave one out? Nav antennas. Nav antennas, we're investigating a couple different locations for those. One possibility is a blade-style antenna located forward of the leading edge of the wing. They will serve a dual function of both nav antenna and vortex generator. I think I got them all. I'm sure I missed one or two. The question is, what can you tell us about avionics? Not as much as we'd like to. There's a lot of, it will be a Garmin avionics, integrated avionics system. It will be an evolution or a growth off of the Perspective system. There are new things that we just can't talk about.
Let me comment on that. Some of the new things that we just can't talk about are things that some of them we don't even know about. Avionics is one of these. Just look at the last 5 years and how much change has been in SR20, SR22. So the way I really look at this is the base avionics, like as we say, Cirrus Perspective. If you think of the core functions, the boxes, we can freeze those in the next 6 months to say 12 months, and then we can wait a little longer for some software and some I/O and user interface. So that's part of the hard part for Dave, is we're thinking about all kinds of things here, and we really don't know the right answer to that. So if we say it's going to be XYZ today, I'm sure tomorrow we're going to be wrong. So it's premature for us to really say, but it will be multiple screens. I mean, when you say multiple screen, I'm not talking about two PFDs and an MFD, but it'll be multiple screens with, for example, probably backup instruments will be a screen instead of a two pneumatic and a backup attitude indicator. So, and then variations of input devices. That's the part that is the user-friendly fix, is how do we get the user interface devices, the I/O devices, to be the easiest to use. We're working very, very hard on that. We have a document that's called PVI, or Pilot Vehicle Interface. That's I don't know, about 80 pages. And the way we developed that document was one of the methods we used was we took I think it was about 15 pilots, I'm not really sure, that we felt like had internal and also some of our suppliers. And we gave them a list of all the controls and indicators in a typical SR-22. And we gave them a flight scenario. The flight scenario included flight over mountainous terrain, you run into weather, you have to divert, you do a missed approach, and things like that. So that was the mission. And then we said, now go down this list of controls and indicators and say, how many times do you use this control? And then is it a critical function? And they each independently did this, and we collated that and came up with these controls that we call frequent and critical. And those are the ones that we focus on for ease of use. So, I mean, you can imagine tuning a comm. That's very high frequency. So we want to make sure we get that right, we get it easy to use, those kinds of things. So we're still working on that. Can't really, it would be speculating if we tried to answer that.
Full fuel payload at that 3,700 pound target, that would be 400 pounds. So we plan on 3,700 pounds. We're shooting for 3,600, so it would be closer to 500. And we're expecting a 1,900 pound usable fuel capacity.
It'll be 3,600.
That's 1,000 miles NBAA range with a 100-mile diversion plus 45 minutes reserves. The question is de-ice system, and we mentioned that we're doing inflatable pneumatic boots in place of a TKS. And why would we do that? Well, the answer is the speeds that this airplane flies. One of the factors that determines what your flow rate through the TKS system is true airspeed. It relates to the catch rate or the accumulation rate of the icing system. In order to have enough fluid to handle the accumulation rate at the speeds that this airplane has to fly would be a lot of fluid. And that relates to a lot of weight, a lot more weight fraction, a lot more relative quantity of fluid that you would have to carry in this airplane versus an SR-22. So it's really not practical in this performance range of airplane. And that's why you see a lot of airplanes, a lot of the light jets, well, all of the light jets have boots.
I think Paul just left, but he would be able to answer this better than me, but I'll take a crack at it. I think our goals are a 2-week course. We're not sure that that's going to be doable, and the requirement will be IFR, but not commercial. It has to be IFR for the type rating. That's just a fact. So the 2-week is an aggressive goal. We're trying to bring the flight training devices into this as part of that. We know that there will be airplane time required, so we're trying to set that airplane time requirement as low as possible. And I think it seems to me the number that Eclipse baselined this. So I think that number was 16 hours, but I'm not really sure. So. But that's the kind of the parameters we're working around. In the airplane, yes. And there's other, the simulator will be our goal to do much of it. And we'll do the similar kind of thing of profiling the pilot prior to coming, so you know where they fit into the syllabus properly and what syllabus to actually give them. So that's part of the work that we did with Bob Wright early on. I think we're about at, we'll take one more maybe. The question was discussion with the insurance companies. I personally haven't done that, but just a couple of days ago I was in a meeting where Gary Black, if you know Gary Black, he's our jet sales. He told me that he was at somewhere where he sat down with an insurance broker and talked about this. And our goal of a low cost, and I'll say just for sake of a middle ground here, is $1.2 to $1.5 million airplane. That hull value is going to help keep it down. On the other hand, up to 7 souls on board is more than an SR-22. The type rating helps because it has the requirements. So they went back and forth and talked about this, and I didn't get a real number, which I don't think we will get from insurance companies until we actually start delivering airplanes and customers start wanting to get insurance. So I don't know the real hard number, but we have had some discussions. We just haven't really quantified it very well. Okay, I think that's all we have time for, so thank you for coming.
Thanks.
For those still on the live broadcast, let me go over the schedule for tomorrow. The stream will be going down pretty soon now, and hopefully come up around 8:30 a.m. for Alan Klapmeyer, who will be 8:30 to 9:30. 9:40 to 10:40 is John and Martha King. 10:50 to 11:50, and be George Braley for Tornado Alley. The lunch break is 11:50 to 1:30. 1:30 to 2:30 is a Cirrus Perspective and Garmin update. 2:40 to 3:40 is Cirrus ownership, and 3:50 to 4:50 is Ask Cirrus Engineers Management and Sales. With that, we're going to turn off the box. I hope you had a good day watching the stream.
Yeah, shift delete, that just gets it straight away. And then I'll just run my little program and get it back. No, it's